Okay, so in this video, I'm gonna give a quick briefing about Lab 2. So I'll go over some of the theory part, which is also in your lab manual and the associated videos, but I'm just gonna go over it a little bit and maybe give a quick context for the lab. Okay, so last week we talked about voltages and currents, but when you did the lab, you generated and measured sort of a constant voltage signals, so voltages that don't change over time, and these are called DC signals, short for direct current. But this week we're going one step further and looking at time varying signals, so signals that vary in value over time, and we're going to learn how to generate them using waveform generators and measure them using DMMs. Okay, so that's the goal of this week. So talking about time varying signals again, these are signals that change in value over time. All right, so in general, these can be any shape, right? Um, it can take any value and it's changing over time. But we'll start by looking at a special case of time varying signals called periodic signals. What that means is that the pattern or the values that the signal takes, it repeats after a certain period of time. And such signals are called periodic signals, okay? And we're going to characterize these signals by 4 or 5 different uh, parameters, okay? And the first being is the shape. So it can take on different shapes. Second is frequency and period. So like I said, the pattern repeats after a certain period of time. So the period of time after which it starts to repeat is called period, and it's 1 over the period is the frequency. So it gives you a measure of um, how many cycles per second you have. Average is if you take the average of the signal, then it's going to be somewhere in the middle right here. So that's a measure. Amplitude is the maximum displacement from the average. And RMS is something we're going to discuss in detail. Okay, so again, shape, you can have different kinds of shapes. You can have a sinusoidal shape, you can have square wave, triangle wave, sawtooth, and even DC you can consider it to be a shape. It's just um, not a very interesting in terms of time varying signals. Period is measured in second. Frequency is measured in cycles per second, or its units is hertz. Um, Average, like I said, it's the time average. And so what you do is you sum the voltages over time and divide by the total time, right? Since it's a periodic signal, you can sum it and divide it by the period of the signal, which is t. Okay, so this average has many other names. It's sometimes called the offset, sometimes the DC offset, sometimes the DC component of the signal. It goes by different names, but they all mean the same thing. It's the time average. Amplitude. Again, amplitude is the maximum displacement from the average of the signal. There can be some like confusion or ambiguity with the term amplitude, because there's something called the peak-to-peak amplitude, which is, well, the distance from or the displacement from the max to the min, right? Some text will use this to be the definition of amplitude, and some will use this to be the definition of amplitude. And you just have to be careful in reading your texts or using your equipment what definition of amplitude they're using. But most commonly, the definition of amplitude is this displacement from the average. Okay, and so if you look at a mathematical representation of a signal, right? It will look something like this, okay? Um, so you have voltage is A sine 2 pi ft plus B, okay? And in this mathematical representation, you'll see all of the features, right? You start with the shape. You have, it's a sinusoidal shape. You start with, okay, how do I, so that you can join without me? Okay. Okay, yeah, so you can see the shape, which is sinusoidal in shape. You can see the frequency, you can see the DC offset, and you can see the amplitude. When you're writing a signal in a mathematical representation like this, there's no ambiguity in what this means. This is always the peak amplitude, okay? So this amplitude. It is never the case that this actually reads peak to peak amplitude, okay? So that's the good thing. There's no ambiguity there, okay? All right, so now let's talk quickly about RMS. So RMS comes from this idea of power in a signal, okay? So for DC signals, we looked at power and we said that the power is simply the product of voltage times the current. And if it's across a resistive load, then you can replace the current with V over R and you get V squared over R, right? For time varying signals, you can do the same thing, but now the power is going to be a function of time, right? Since voltage and current are also changing as a function of time. So this is what we call the instantaneous power, right? So at a particular instance in power, what is the power? What is how much energy is being dissipated, right? That's what we call the instantaneous power. Now, if we talk about the average power, again, what we're going to do is take the integral of the power over the period of the signal and divide it by the total period. Okay, that's how we take the average. And if you do the math, then you'll end up um, with this expression, right? You have 1 over R and the average of the voltage squared. Okay. Now this whole thing is a constant, right? Once you have taken you've taken the integral over time, there's no time variable in there, and that's a constant, and it has units of v squared. So we can replace that um, with some voltage squared. Okay, some I'm just replacing with some variable voltage squared. Um, so then you can contrast this expression with the power expression for the DC, and it's exactly the same, right? So what this means is that this voltage that we replaced here, that's the DC equivalent voltage, or sometimes called the power equivalent DC voltage. What that means is if instead of this time varying signal, I had a voltage of this value uh, being applied across a resistor, the DC voltage signal would dissipate the same amount of power as this time varying signal, right? So so this voltage is a measure of the power being dissipated by the time varying signal, but measured in voltages. Okay. Um, so if we take it a little bit further, you can see that this voltage squared is equal to this integral, and take the square root, what you get is you get the root of the mean of the square of the voltage. And that's what we mean by root mean square, okay? Root mean square voltage. And so root mean square voltage is the term that basically describes this operation, but uh, why it's significant is because this voltage, this number, gives you a power equivalent DC voltage for that time varying signal. Okay, so and again, just rewriting it, power at the average power of a time varying signal is then the RMS voltage squared over resistance. Okay. All right, so quickly doing an example for a sine wave, let's say we start with this expression. It is a pure sine wave with an amplitude of A. If you put it into this expression, what you get is the RMS voltage is A over square root of 2. Okay, so just make a note that this is a constant in time. And, and so this result you can use whenever you want. Okay, so you don't have to go through this integral again. So if you see a sine wave with a particular, with some amplitude, then its RMS is that amplitude divided by square root of 2. Similarly for triangle wave, we can do the same exercise and the result you get is A over square root of 2. For a square wave, it's just the amplitude of the square wave. Okay, but now what if that sine wave had a DC component associated with it, right? Then you have to do that. We can do that integral again, and you can do the math. I'm skipping the algebra here, but what you end up with is you end up with this expression, square root of a squared over 2 plus b squared. And if we massage that expression a little bit, what you will see is that this is basically the RMS of just the AC part, right? Just the sine part, and this is just the DC offset square. Okay, so so this is the RMS of the overall signal with the AC and the DC component. Okay, and this is the DC equivalent voltage for RMS voltage for this overall signal, and which is why it's also sometimes called the DC RMS. Okay, so it's the DC equivalent RMS voltage. But if we break it down into the AC and the DC offset, what you will see is that the DC RMS squared is the sum of the AC RMS squared and the DC offset squared. Okay. So this DC RMS is also sometimes called the true RMS or the overall RMS. Okay, so just don't confuse DC RMS with the DC offset. They're two very different things. DC RMS is, well, it's an RMS measure. DC offset is simply the DC component of the signal. Okay, so just to remember this expression, you can think of it in terms of Pythagorean theorem, where you have a signal being composed of the AC part and the DC part. But when we take the DC RMS, it's as if you're summing the two base and the height of the to get the hypotenuse of the right triangle. Okay. All right. So, for example, if I have a signal like this, then what would be its AC RMS, right? So what would be its DC RMS, right? And the answer is, well, it's you can either do that integral to calculate the DC RMS, or we can break it into the AC part and the DC component and do the AC RMS first. AC RMS is the RMS of just the AC part. So that would be 2 over square root of 2, since it's a sine wave. And then the DC offset would be equal to 3, right? And so then the DC RMS squared is the AC RMS squared, 2 over square root of 2 squared plus 3 squared, which would be, so this would be 2 plus 9, which means that DC RMS is equal to square root of 11. Okay, so this is how you would calculate the DC RMS for a signal, right? No integrals required. Just have to know the fact that for a sine wave, the AC RMS is the amplitude over square root of 2. Okay, any questions so far? Okay, so then next we'll start talking about equipment and instruments. So I don't know if you have the 82 yet or not, but I'll just go over this really quickly. So 82 is not one instrument. Okay, so 82 has um, 6 or 7 different instruments packaged into one single package. Okay, um, so all of the instruments that you will need, except for the DMM, is in the 82. Okay? So if you need a power supply, it's in the 82. If you need a waveform generator, it's in the 82. Okay. Um, if you need a voltmeter, there's also a voltmeter in the 82, but you will be using a DMM because this DMM has more features than the 82. Okay, 82 only can measure voltages, it cannot measure current or resistance, and so on and so forth. Um, it has an instrument called the oscilloscope, which you will be learning about in Lab 3. Okay, for this lab, if you are doing the 82 version of the lab, the hands-on version of the lab, then what you will need is the waveform generator, and that's it. Okay, and maybe the power supply for one of the tasks. Um, okay, so then we'll just, well, yeah, so the DMM has different modes that you've already explored in lab 1, but in this lab what will be new is the AC voltage and AC current features. So these will measure the RMS um, of um, of the time varying signal. Okay, but the question is, does it measure AC RMS or does it measure the DC RMS, right? Um, and this answer can depend on the DMM that you're using. Okay, and you should be able to figure that out, given you're generating a particular signal that you know what its DC and AC RMS should be. Okay, now let's just briefly talk about how you would build circuits, right? Because sometimes I've realized that students who haven't done this before can have struggles with trying to build circuits with these equipments. Okay, so for example, here I have a circuit with a 5-volt DC supply being applied across a resistor, and then you have a voltmeter connected to it. Okay, so this is a measuring instrument. Okay, so the actual circuit, the operational circuit is just this much. Okay, so we'll first start by constructing the operational circuit, and then you can add the measurement equipment later if you want. Okay, so first of all, we need to figure out what you're going to use to generate the 5 volts, and the answer is the power supply unit. Okay, so the power supply unit in 82, you will set that to output 5 volts and enable the output, and then you connect the V plus to the resistor, right? And then that's connected to ground. Okay, don't connect it back to V minus. Okay, so this is another power supply output unit, output terminal, not the ground. Okay, so current will flow from the power supply unit through the resistor to ground and back like that. Okay, so this is connected to the power supply unit. Um, this is a common ground. Now, once you have the circuit completed, you can add your DMM to measure the voltage across the resistor. Now, when you're using the DMM, just make sure that when you're measuring voltage, you're on the voltage port and you've checked the voltage. You're on the voltage mode of the DMM. Otherwise, you can do bad things to your DMM. Right? I don't want you to have to buy a new DMM because you broke it. Okay. Now, similarly, if you wanted to measure the current, it said, right? So you build this circuit, but now you want to measure the current instead of the voltage. What do you do? Okay, so this is a slightly different example because now you have a time varying signal. To get the time varying signal, you can't use the power supply unit. You have to use the wave gen, okay, wave generator or arbitrary wave generator. And these signals come out on pins labeled W1 on your 82. And this is also reference to the common ground here. Okay. So yeah, so you're going to set up the wavegen to output amplitude of 3, frequency of that, everything as you need it, and then connect that to the resistor, right? But you want to measure the current, so instead of going directly to the resistor, we'll go through the ammeter to the resistor, okay? So you'll connect waveforms 1, W1, to the positive end of the ammeter. The negative end of the ammeter can then go to the resistor. And then the resistor connects back to the common ground of the 82. Okay, so that's how you can build the circuit. All right, any questions? Okay, so if you don't have the 82, you'll be doing an LT Spice version of the project, of the lab. And in that case, well, if you haven't already, you need to download the LT Spice and build your circuits and do the measurements by running the simulations. To measure RMS, well, you'll have to run the simulation, and on the simulation results, well, actually, I might be able to show it. Actually, yeah, so the LT Spice tutorial will go over how to measure RMS on your LT Spice simulations. Okay, so I think that is going to be all from my side. If you don't have any questions, I will stop recording. Okay, so I'm just going to give you a quick demo of the LT Spice. Don't worry if this circuit doesn't make any sense to you right now. I just want to show you how you can measure RMS on LT Spice, right? So first of all, you can build a circuit like this. Then you would do a transient simulation to, well, whenever you have time varying signals, you want to do a transient simulation so that you can observe the signals over time like this. And to get this plot, you simply have to click on the node voltage that you want to plot, right? So if you wanted to plot this voltage, I would simply click here or here. Okay, so this gives you the voltage over time. Now, if you wanted to measure the RMS, what you have to go is control click the label over here, and it will give you the average as well as the RMS. Okay, so that's how you can measure RMS voltage on LT Spice.